All right, good evening. Today we're going to continue our work on the NFL Big Data Bowl. The plan for today's stream is first kind of recap everything that we've done so far, so that way if this is your first time seeing it, you'll have an idea of everything that we've done, what our plans are for how we're going to put together this for the Big Data Bowl. That should probably take about the first 20 minutes. Then we'll work on adding information about the receivers or pass catchers on a given play, as well as the defenders and their coverages. Then we'll do some visualizations on those just to give an idea, very similar to how we did for offenses in terms of their play percentages. We'll add some visualizations around that receiver and defender data, and then we'll work on adding those into the models. I'll explain a little bit about the models when we get to those sections, and then we'll wrap up for today and cover next steps. All in all, I would expect this to go for about an hour and a half, maybe to 2 hours, depending on how long it takes for some of the models to run. Right now, it's running the notebook since the beginning. It's been running. Some of the models take about 5 to 10 minutes for it to run, as we're generally using smaller data sizes for the models. But it may take a while when we get down to doing the model section to make those iterations. So I'm hoping that adding the receivers and defenders to the models won't change things too much, as right now, the models that take in that 5 to 10 minute range are the ones that have the players for the offense, all 11 players on there. And I don't think it adds a lot knowing things like who the linemen are. And that's why I want to shift it to just knowing who the pass catchers are on the play and the quarterback. And then the knowing the defense, it may just start with, things like who is the opposing team. I don't think we have that in the model yet. And then the defensive formation information, similar to how we have that for the offense, and then potentially adding the players. But I think it's going to be another similar situation where actually in general, knowing who the players are actually cause the model to perform worse than it does without that information. So we'll go through, like I said, we'll add the receiver and defense information, then we'll add those to the models, and then we'll try and get a better understanding of what's working and what's not and do some experimentation there. So let's get into the recap of what we've done so far. So the goal of this big data competition is to use the pre-snap information to predict the post-snap information that you would get. Think of this like, you want to use everything that happens before the ball is snapped to try and predict whatever it is you like out of what's going to happen afterwards. You could do things like we started with, just predicting whether a play would be run or pass, and then working on expanding that now into, we're trying to use this to predict the route combinations on a play. What you'll see here is that becomes much more challenging of a goal, because there's way more options, right? Run versus pass is very binary, right? You're either going to run the ball or you're going to pass the ball in terms of what you're going to do. Now with the route combinations, you're already assuming there's a pass. So we haven't even tried to do run versus pass and then what they would do in the pass. We're merely just trying to, on a given pass play with these on a given pass play, try and predict the route combinations that you will see here. But that's like, there's so much more that you could do post-snap. You could choose to highlight specific players, and what they'll do, you can kind of see this a little bit when you're watching football on TV. You kind of know who the big players are to look out for during the game. Certainly defenses would also have that in mind, but you can see kind of how different defenses are reacting to them, or vice versa, where it's a key player on the defense. Is the offense going away from that player? How do those interactions actually work out here? So it's a very open-ended competition. Usually the Kaggle competitions here are, you have a very specific goal in mind. Like there was like the Titanic, predict who the survivors would be with the highest amount of accuracy, or there's a housing market data set where you try and predict the value of a home based on the information that you have. And this one is more open-ended and nebulous, and that's I think one of the fun things about this competition compared to the others is it's not necessarily that you have the most accurate model. I would focus more on having your model actually be explainable, because your target audience here is not the accuracy for what you're getting out of here. Your target audience is actually going to be people who are NFL coaching staff members. And that's actually one of the groups that you can go into. There are 3 tracks. One is the undergraduate, which, because I'm no longer in school, don't qualify for, so we won't worry about that one. There is a metrics track where you're trying to measure certain information. And then there is a coaching track where your target audience here are coaching staff or coaching staff members of NFL teams. And so you want something that, I think the goal here is something that is quick and can effectively explain things very quickly. So you don't want something that is very black box in terms of what it is. And you'll see that's actually one of the models that we have here, just as like a baseline comparison. Something like random forests, where it's really hard to work backwards on why you made the prediction that you did. You can't really see like what the factors are easily that are affecting the model. And so that becomes harder than when you're talking to an audience who's less technical in terms of the data science and far more technical in terms of the football. So what we actually did for the run versus pass is we started with logistic regression. The thought process behind this is that you have a very binary outcome, right? Run versus pass, which is perfect for logistic regression. But it also then, from the coefficients of all of your variables in the model, you can tell what is a powerful predictor of why it chose run versus pass. So you may see things like, oh, you're against, and I'm just going to pick a team at random, you're against Cincinnati. And so you're choosing to pass the ball more because their secondary, or their the yards that they give up via passing is higher than it would be if it was, let's just pick another team, Pittsburgh would be against the pass. So then one of the biggest factors could be that your team that you're going up against is Cincinnati. And so it's more valuable and more likely that you will be to use passes. So that was why it would predict pass instead of run. Whereas against Pittsburgh in this example, you would choose to run more often. And so the coefficient for Cincinnati is higher in terms of predictive outcome than it would be if it was a team like Pittsburgh. And these are just purely examples. They're not actually what we see here in the data. But to give you an idea of kind of what our goals were, we got to a 75% accuracy on run versus pass, with just some very basic information. And the return time on the model is also very fast, not just in terms of making the prediction, but in terms of building out the original model as well. So you can quickly adjust to the data almost in real time on the given game that you're watching. So just to cover everything that we've done so far, this first part here is merely just loading in the modules that you'll need, or the libraries that you'll need to run the code for the functions here. And then these are your data sets. So there is the game data that includes when the game was played, who the teams were, what the score was. You have the player data, which is the statistics around the individual player. So it'll have their ID, their name, what college they went to, how long they've been in the league, what position do they play, and I think their number. And then there's the play information, which is for each individual play, it will be like, I think one of the first ones we see is like Joe Burrow passed to Jamar Chase for 8 yards over the middle. And so that tells you, it's like the sentence description. So these will be things that you will see kind of in the live feed if you are watching the game on like a stats cast or something like that, where you're only getting the statistical information. You're not getting like the video feed, and that tries to substitute for those. And then there is a player play data table, which is on a given play, who are the players that are on the field and what is the information about them. So this is the largest table by far, has the most columns, the most amount of records. And the reason for this is that there are 22 players on a given play who have to have some information about them being tracked. So who made the tackle on the play, who was blocking who, what route was the receiver running, what was the defensive coverage. There's quite a lot of information here, and this is the backbone of what we're going to be using for our model. There was also the weekly data here. I had not chosen to use it for anything so far, merely just using the player play data to use this for prediction. This has the field tracking information for every player during every play of the game. So where are they on the field? How fast are they going? Where is like the ball relative to them? It's very detailed information, and these are each individually quite large pieces of data. The first video in my series then covered just going through and doing some data exploration. We weren't in a rush to build any model. We wanted to make sure that we understood what the data is, how it's formed in the tables, so that way we can have a better understanding before we go and try and build some models. So the first thing here, this is just a remnant of one of the many things that we did, but this one was checking for the plays table, how many fields are null, and then give me the total of them in it. So it's a good example of what the data set would look like. Here, we have a very complete data set. If you're working with this data in the real world, it would be, the live stream from the game itself would be much less clean than what this is. I'm pretty sure that they spent a good amount of time like sanitizing this data set to make sure that a lot of the outlier information has already been taken, not necessarily outliers in terms of performance, but like, oh, there's missing information on a given play. At this point, the data set is pretty complete, and you see that here, and that's why many of these columns have a lot of zeros. What this means is that these all have this information filled in. So the play description was the thing I was telling you about. Like, for the example, it was Joe Burrow for an 8-yard pass to Jamar Chase. The possession team is the team with the ball. Defensive team is the defense on the play. Yard line side is there are 224 rows here that are null. This is because these are the plays that happen on the 50-yard line. And so that technically does not have a side that is the middle of the field. And so there is no information on those plays. That's part of why you see this here. But for the rest of them, there's all information here. And you can see here, so yard line side has 224 rows, but yard line number is 0. And so here on those specific where the yard line side is null is because the majority of these happen at midfield, and so there is no yard line number on that given play. Or sorry, there's no yard line side on that play, but the yard line number would be filled in as 50. Game clock is the time in the game with the respect to the quarter. So if it's the first quarter, it will say just 10 minutes. If it's the third quarter, it will still say 10 minutes. It does not account for the quarter at all. Then things like the scores, play, penalty, the absolute yard line number, so how many yards to go to get a touchdown. And then there's more information here. Offensive formation, receiver alignments. These actually turn out to be kicking plays where there is no offensive formation or receiver alignment there. So that's why those are actually null when we looked into those. You can see here the play result length. Those are only for pass attempts. Would you have a pass result? So there's like 6,300 rushing plays. And then the pass length, there are a significant number of incompletions in the data. Who the target was, again, on those rushing plays, no target for those because it's a rush, it's not a pass. And then we started to kind of get a better understanding of, now we know what the tables look like. What does the data in those tables look like? So then quickly trying to get an idea of what the average rush yards are. If you just try and do this directly, it will tell you that the average rush is 0.09 yards, which isn't right. What is actually happening here is that there are 22 players on the field. Only one of them has rushing yards. So that significantly will bring down the mean far closer to 0 than whatever any rusher can do. So then we looked through the data set and we found that there is a had rush attempt flag field, and if it's 1, that means that that was the rusher on the play. They will have the rushing yards, and then getting a mean of those gives you that there are 4.56 yards gained per play in the data set that we have. A very similar thing happened for receiving yards. So we went through the same thing. We found out that that was the had pass reception, so who actually caught the ball on a given play. But be careful, because this is who they had to have caught the ball to have receiving yards. So this is not your average yards per pass attempt. This is average yards per reception. That'll come in important later, because some of the initial models that we were building for run versus pass, the player had to have a reception versus an incompletion. And so that caused some slight changes in our model performance once we shifted those correctly. Then this query here basically ends up being, how do you know who the top 5 offenses are by average yard per rush? So you see here, Chicago, Vegas, Seattle, Jacksonville, Baltimore, and then who were the worst 5? Well, you had Tampa, Los Angeles, Indy, Cincy, and Denver. And the same thing for pass reception here. Don't need to go into all of them, but you can see here just the average pass completion yards gained would be this, and then we'd have to go back and check had passing attempt and see what those yards actually looked like. The reason why you can't use had pass attempt here is because the quarterback gets the pass attempt, not the reception. So the receiving yards don't go to the quarterback in the data set. So you have to get this information, you can only look at the passes that are caught. You'd have to do a bit more manipulation, and you'll see how we do that for the model to get the average yards per pass attempt. Then did some grouping just to get an idea of what it looked like on the individual plays. See like who had the most average rushing yards. And what you see here is these numbers were really high. And then I pulled in, okay, how many rushes did they have to have a 40-yard average? Like you would do that every time based on the data that you had here. And what we saw is that most of what's happening here are these are the outliers in the data set. They may have run the ball once or twice on a trick play. And that's why we are seeing such high average rush yards or extremely low average rush yards. So these are essentially outliers in terms of the numbers of attempts and are throwing the averages we had a line. So then I picked an arbitrary number of 10 here. You could pick whatever number you liked. You can see here, even doing 10, the next close, or the least amount of rushes here is 11. And you can see there's a player here who qualifies because we set it to 11. You can change it however you like. You can see here also like Dontrell Hilliard ran 17 times. So if you set this to 20, 2 of those would drop out of the data set, and you'd have a better idea of who the best rushers are based on that. There was a flag field here, which we would use when we started to build the model just to check and see, is there motion on a given play, and adding that into our data set fairly early, just so that way we can know if anybody had moved on a play, not just the players who had the drop back or pass reception. So that's why we had to do it now before we started to filter down the data a little bit more. The next couple lines here are going through how we're actually grouping the information together. So we had the had pass attempt, and this is what I was talking about before, and the had pass reception. So to get the actual receiving yards over to the quarterback, you have to go this way in terms of the model, where you have to get the drop back to get the quarterback, and then you have to merge it in based on the game and play ID to know who got the who was the quarterback and how many yards did they get per attempt. And then we pulled in more information like what's the name of the actual player on a given play. What was the offensive formation? You can see here pass result, receiver alignment, quarter down, like more of the game situation information, which we will use in our models. Then we went through and in one of our later versions of the models, tried to see if it would actually help us to know who the given players are on a play during a game. And what we actually found out, and we'll scroll down here and show the results from the models, is that knowing the players in the play did not actually help the overall model performance. It added a lot of additional compute time needed to know who the players were. Here you can see it took 30 seconds to figure out who the players are across the whole data set. But then you'll see the runtime for the models go from a minute or two to 5 to 10 minutes as well. So adding overhead. Now I'm only running things locally on my laptop. It is not a top of line machine like you would have during a game. But for people who are kind of just casually following the sport, you could run this on your own laptop and get very similar performance as what I have, as I only have 8 gigs of RAM on this computer. It does have a GPU, but it becomes slightly better by using the GPU, but not enough that it's like some supercomputer like you'll see companies using for this information. And then the other information here was just joining in who those players are back to our data set and merging those all together. And so you can see here, this starts to show you, for example, this play here, Tom Brady was the quarterback. There were no receiving yards because it was a rush attempt for 0 yards. But we know who all the players are here by looking at players 12 through 11. In one of our later versions, we went back and we created some visualizations here. So looking at each team individually, just looking at the formations that they're running their plays from and how they actually approach their offenses. And what you'll see here is that a large portion of teams were running out of this, or were using shotgun and then like single back as their 2 primary formations, with a few exceptions. And those are Atlanta and Baltimore here. So they were running the majority of their offense out of that shotgun, but then the pistol was the next best instead of using the single back formation. So slightly different look, but that's why you'll see these large red bars here. A few other teams ran pistol as well. You can see like beyond just a few kind of gadget plays here and there. So you had Arizona, Philly, Seattle, San Fran ran a few as well, and Washington. But for the most part, you can see a lot of these other teams very rarely ran the pistol formation, if at all. And then to give a better idea of how teams did offensively, I put together this visualization. It's fairly straightforward once you understand how this works. So these are teams' offensive performances. Going left to right are your average rush yard attempts. The blue line here is the NFL average going through the middle. And then going up and down are your average pass yards. You can see, again, the blue line is where the average actually is for each team, or not for each team, for the NFL as a whole. And the goal here is actually to be in this upper rightmost quadrant. This means you had above average rush yards and pass yards. You know, the closer you are to these lines, you're barely above whatever that respective average is, but then it's usually balanced out by you did much better in one aspect of the offense versus the other. So you can look at, for example, these teams here. You have San Fran, the Philadelphia Eagles, and Kansas City, all really close to the average rush yards here, but you'll see that they are then above average in terms of the average pass yards. Now, again, this is based on completions. This is not based off of the passing attempts. So just so you have a better idea, and then the biggest outlier here, you would say, is Chicago or Atlanta. And Atlanta and Buffalo are pretty close to one another in terms of like the top offenses, but on a yardage basis. And then you wouldn't want to be down here in the, we'll call this the bottom left corner. These are kind of the yuck zone of where you want to be, especially over here. So you can see that you had Tampa, the Rams, and then the Colts here with, I would say, overall below average offenses. So Tampa here, barely 3 yards per rushing attempt. And then when you get here to the passing yards, you can see they're also below average as well. Now, a lot of times in the NFL, these two are highly linked to one another. So the better you are on rushing, you'll also be better on average. That's why you see kind of everything here kind of grouped more together on a horizontal slant, or sorry, on a diagonal going through here, rather than things being kind of more horizontal. So what you see is a lot of times, like, you don't have extreme outliers in a very very, very poor rush, but a very high pass, and very similarly over here in this corner, a team that is very, very poor on pass, but very good on rush. You just don't see those. So these two are highly linked together, and that's why they kind of fall. If you were to put a diagonal dotted line going through here, you would see that a lot of teams are more in line with that axis than it is that they are going, horizontal or vertical. Then we started to get to building the basic models. There were a few fields that we needed to create along the way here. We wanted to, for the run versus pass model, make a flag field that told us whether it was actually run versus pass. So that way we could then split the data set however we liked and use it to actually make the prediction here. So if they had rushing yards, it was a rush attempt. Otherwise, it was a pass attempt, basically. And then the very first versions of the models, we used only 3 fields in terms of actually making the prediction. So we had the offensive formation here, the team that it was, and the receiver alignment on a given play. Now, a lot of times these are very much linked to one another in terms of offensive formation and receiver alignment. You can think like the single back field. There are slight variations. You can have like 3 receivers on one side, 1 on the other, or 2-2, and balance things out that way. So that actually did add a little bit of power. But just knowing that these 3 pieces of information, you get a model that is a little over 70% accurate in terms of run versus pass. So just knowing what the team is that you're going up against, what the formation is, and how their receivers are, will give you a good idea on what's actually happening on the play. Ooh, sorry. And what you do see here is that adding more information should be useful to the model because there is quite a bit of variance in predicting run here versus pass. So that's the difference here in these precision recall scores. You can see the average should be closer to around that 70% here, but then these are a little bit out of line for those. You're off by like 3%. So adding more information should get you closer or get you better model results. That should take you hopefully up towards predicting more correctly your answer. So then we expanded it and we added some of that game situational information. Tried to do a few different things here. So knowing the actual score differential on a given play, you hear a lot of times like you have to change your game plan in the 4th quarter when you're down 2 scores. So trying to see, did that actually did that actually hold up, and did that lead to then better performance? We did some experimentation around using a bucketed version of yards, calling it short plays, medium plays, and long plays, versus using the actual numeric values. And you'll see it depends on which model that you're using, whether you get better output here. Same thing in terms of the absolute yard line number. The idea here is the short is the red zone area. You have about 20 yards or less to score. The long is arbitrarily set at 50. Realistically, you would want to set this maybe towards 40 or 35, depending on how good your kicker actually is in terms of those longer field goal attempts. And then creating our own game time remaining. Back at the beginning of the session, I'd said like the game clock doesn't actually tell you information beyond the current quarter that it is. So there's a huge difference, right, in between 10 minutes left in the first quarter and 10 minutes left in the 4th quarter. So adding this game time remaining is just basically adding numbers to those. So you have here in the first quarter, you're going to take that 10 minutes, you're going to add 45 minutes to it, right? Versus if it's the 3rd quarter, you're only going to add 15 minutes to it. So that's the better, get an alignment on how much game time is actually remaining in the entirety of the game. And then you'll see this when you watch football a bit. There are 2-minute warnings at the half and at the end of the game. So we created buckets for those. The final 2-minute warning here is the 2-minute warning that happens in the 4th quarter. There's only 2 minutes total game time remaining left. And then there's the halftime 2-minute warning here, which these are the plays that happen basically with 30 minutes remaining in the game to 32 in terms of the overall game time. But these are the 2 minutes before the half, because the possession will restart at the end of the half. And what you see here is there's about there's about 13,000 total plays that run over the course of the game. And actually quite a bit happen here at the It's about 10% between halftime and the 2-minute warning. And then you see here that there's actually more plays before halftime. And the reason for this, when you think about it a little more, makes sense, is because you can be at the final 2-minute warning and one team will be up by 2 scores with the ball. So it's impossible for the defending team to win. They simply kneel out the clock. They run those 3 or 4 plays in that 2 minutes of time. And then the game ends there. Versus at halftime, every team is trying to score to add more points here. So that, because you're going to get another chance at the in the second half to try and either make your lead larger or to get closer in the game. So that's why you see that there's actually about 40% more plays in the halftime 2-minute warning versus the final 2-minute warning. So I'll pause here for a moment, just grab a drink. If you have any questions, feel free to add them in the comments or the chat. All right, so then adding these new fields to the model gives us different results, right? So add those game situation information, what quarter, what down, the yard buckets here, distance is the number of yards to score, was there motion, how much time is left, and then the score differential here. So once we put those in, you can see just that same logistic model now goes to a 74% accuracy, which is great. And looking here, you can see that the precision recall scores are much closer together. So it's far more accurate in terms of its overall prediction. There's less fluctuation here. And then doing another version where we add in the player information. Like I said, this takes a bit longer to run, but what you see here is actually we decrease slightly in terms of the overall model accuracy. Then we looked at this. Instead of using those yard buckets, we're just going to treat them on their actual numbers here. So you got yards to go and an absolute yard line number. And what we see is that our model accuracy goes up. So it was 74.1% before. Now we're at 74.4%. So improvement there by using the actual numbers instead of using buckets that we had set. This may just be that we need to define the buckets a little bit better, or maybe it's just not worth it and we can just use the yards directly. Then doing the same thing with the player information, we get slightly better results than before when we knew who the players were, but still not better than not knowing who the players are on the field. So actually knowing who the players on the field hurts our model performance. We go from 74.4% down to 73.8%. So knowing who the players are didn't actually help us in terms of our model. And then we started to build out a few more model types just to kind of check to see, is there something we're missing? Maybe there's a model that performs better. So we went with random forest here. This is the one where it's harder to explain what's happening, but should fit data sets much better overall, because it will kind of keep grouping the data until it gets them assigned better based on the number of estimators that you have. And what we actually saw here is when we got the player data, we got similar accuracy to what we had in the logistic model. But then when we did not have the player data, it actually performed worse. So apples to apples, when we use the player data, it's about the same. When we're not using the player data, it's not any better. And then, like I said, if your target audience here is the coaches, you want something that you can actually explain why the model came to the conclusion that it did, especially if the model is going to be wrong 25% of the time. You need to explain like why it went wrong. And here with the random forest, it's extremely difficult to do so because you have no way to easily classify why it predicted what it did. You can work back to it, but it just takes a long time to get there. And then the other model we tried was the support vector classifier. Again, better explainability than the random forests, typically tries to fit better, but what we ended up with are a couple models that actually performed worse. So again, knowing who the player data helped it, but overall it was worse than the logistic regression or the random forests. And then this is where we were last time. We tried to shift into the route predictions. So knowing that is, or assuming it's going to be a pass play going in, can we predict the different combinations that we're going to be run on a play? Here we had to change our data set again. So we needed to know who was actually the home team versus the away team. This helped us then know who the defending team was on a given play. We needed to know who were players that were actually running routes here, and then kind of group those together. And what we see here is that on the, I think we saw there were about 7,000 pass plays before. There's about 2,800 combination, or 28,000 routes that are being run on those plays, right? Because you have one for each receiver or pass catcher on a given play. So you can have about 4 to 5 receivers on a given play. And once you have your 5 linemen and quarterback accounted for, it really doesn't leave you. The most you could have is 5, sometimes usually 4, because you may keep your running back or tight end into block instead of running route. So if we do the same thing but with logistic regression, it should not perform as well because we're no longer in a binary situation. It is still a classifier. You're grouping data into groups, but it shouldn't get as strong performance as what we got before. And we do see that. There are far more buckets here, and we see quickly that the overall accuracy now is only about 30%, roughly, on a given play. And we have, again, using the best performing model that we had before. So knowing how much time is left, what the score differential is, yards to go on yard line numbers are actual numbers here, not using the buckets that we'd set up. Doing the same thing with the support vector classifier, you can see here it's about a percentage point worse than the logistic model, which was kind of surprising. I expected this one to be better performing here, but it's still kind of lacking. And you can see here, there's still a lot of unexplained information because you can see such wide variances across a number of groups here in there. You can see here like angle routes. It's just there's not enough information yet for the SVC to perform well. And so we would need to figure out what we're missing from the model and try and add it in here. And then I did the same test with the random forests. And you can see here, very similar situation. A lot of times when it predicts, there are wider ranges. These are closer than the ranges that we had seen in the other two predictors here. So it's getting, with just that little bit of information, it's closer to being accurate or being more confident in its predictions, but it's not very accurate. It's only 22% accuracy here versus the 30% accuracy of the other ones. It's like this tries to predict more a balanced data set, whereas you can see up here, it's like, oh, I'm not even going to really bother to predict what screen passes, wheel routes here, because there's so few of them in the actual data set. I'll try and say it's something else, so that hopefully I can catch one of those bigger buckets. And then coming around here, okay, maybe it was worthwhile to know who the plays were, because when we added who the pass catcher was, we saw improvement in the models. We went from, we started out around 20% across all of them. This improved it slightly just by adding in who is the individual player that we want to predict for. We weren't doing that before. So very low-hanging fruit, but did improve performance. And then now, okay, who are the 11 total players that are on the field? There will, of course, be some overlap with the player that's here. But you see here, the model accuracy actually went down. We were 29.7% before, and now we're 28% overall. So about 2 percentage point drop. Support vector classifier, this one, it dropped about, I think it was 0.5 percentage point. So it didn't particularly help. But then I was most shocked here with the random forest. This was 22% before, and it actually got a whole percentage point worse just by knowing who the players are. So it's not actually adding useful information by knowing who the receivers are across run versus pass, and now on those route combinations, right? So knowing all the players here adds a lot of overhead, but it does not help our predictive power. Then the most recent video, we added the decision tree classifier here. The idea here is that it can help us to segment the data, hopefully more quickly to get to the right amount of information. And one of the things that we see here is, well, we were working on an individual team here with Tampa Bay just to see if we can get better results, and we don't. So we were doing an experiment to see how many splits we let the decision tree run to try and determine information. And what you see here is 5 splits, it actually is the strongest predictor at about 29%. As you add more, you're actually getting worse in terms of the predictive percentage of the model until it gets to about 22.7%, and then just stabilizes there. So you can see there is almost like a wave pattern in the data here before we plateau off. And you can see little spikes here along the way. So I started 29%, right? Drop down 28, 26, 24, 21, jump back up to 24, up to 26, and then start to go back down a bit, and then ride that all the way down to 21%, and like I said, stabilize at 22%. So kind of surprising that very quickly it got to where the data kind of stabilized just on the number of splits here. So once you said, oh, there can be 24 splits in the data, it didn't add anything additional afterwards. Otherwise, you would use one of these. And so it's saying the best overall is actually to use the 25% here. Will give you the most accuracy. So then we went through and we looked at it a little bit. So I think here, just trying 8 got you to this 26.4% accuracy. Go back here, matches up exactly what we said before. And then looking at this classifier, you can start to see why it did so. So in terms of the overall data set here, there are very few corner and cross routes in the data set, so very little for it to actually go through and predict. A lot of times, in this confusion matrix, I think highlights it the best. He was basically saying that most of the times, I'm just going to predict that it's going to go route. I won't always be right, but I'll hit a fair amount of times once I actually get to the go, because it's the largest part of our data set. You can see very, very similar here with the flat, where it got fairly accurate in terms of this, at least like about 50% accuracy in terms of its performance here, but not the greatest in terms of overall model performance here. Like I said, a lot of times it's predicting its go route just as a blanket for everything. And you can see the ones are a little bit spread around, but not a very high accuracy at all. And then we tried to look at what rules was it using to make those splits. And so what you see here is that knowing the player IDs actually helped it greatly in terms of being able to do those splits. And then this is what it actually looks like once you kind of graph those out. Now, I could zoom in a little bit, but it just gets blurry. But you can see where it's actually making the decisions to separate here along the way. So the max depth is how far down in the table you're allowed to actually go. And what you see here, right? So you go 1, 2, 3, 4, 5, 6, 7, 8 here, and one last split on that to get you to 9, right? So your first split here, your last split here, and these are the final outcomes. As you add more splits, you would see more division overall, but it would, we'd seen from earlier that it would actually stabilize around that 25 depth tree in terms of the model performance, where it's not getting better as you allow it more depth to go. So it's gotten all of its predictive power out of those 25. So what that means is that we should be adding more information to this model, because it's missing a lot of information to actually predict correctly. And that just by letting it split more, we're not gaining anything. And this will change, obviously, as we add more information to the model. So that's kind of a recap of everything that we've done so far. I know that took about 40 minutes to go through everything, but I think it's a good explanation. So that way, if it's your first time coming to the stream or seeing this the first time when it's on YouTube afterwards, that you can kind of get everything that we've done so far up to this point and kind of pick up where we are at now. So we'll pause here for a moment, and then we'll work on going through and getting the pass catcher information. So I'll wait here for a moment just to check if there's any questions or anything in the chats. Does not seem like it. Let me share out as well while we have a second. This is a link to the Big Data Bowl on Kaggle. This is the data tab, so you can see exactly what information you have available to you for doing these. Like I said, we're working mostly off of the player play table in terms of what we're using for our data set. Now we'll go back and we can start to work through getting the pass catcher information. So go up here. So this is where we expanded things for the regression models. Yeah, so let's do the route prediction section. Okay. So like I said, here we have a far bigger data set because there are more route combinations on a given play. The goal here is that we want people to, or we want to be able to predict the routes for receivers on a given play. This NFL IDX is the player on the play who ran the route. Y is their quarterback on the play. So in this case, like this would be Josh Allen here. So we should add that to the model, actually, as that would be useful information to know not just who the player is, but who their quarterback is. So something low-hanging fruit that we could add here. So the reason why I can quickly throw this in here is it shouldn't take too long for this to come back. Remember, we're at 29.7%, but just knowing who the quarterback is should be helpful to that model. And that's like I said, we just didn't realize that we had that before, so why not add it in? It's 12 seconds and didn't actually change all that much knowing who the quarterback is. So 29.70, we're now 29.71. So what is that, like a 100th of a percentage point? Not all that effective knowing who is the pass catcher or who the quarterback is. So let's see here. Go to that. So let's go up here. I want to know offensive player position data. And the reason why we want to do that go to player play. wide receivers, tight ends, running backs, because those are all eligible receivers on a given play. And so once I add that, I just want to take a look at that and then decide what to do next from there. Let's run this. Yep, run. Shouldn't take too long. Is it position? Let me go look at the data set. No, it's not in there. Yeah, it's in the player data. I don't know what I was thinking. There. Players. There we go. So knowing who the players are, what's going on. None of are in the columns. Oh. I think that cleans it up now. So 1, 2, 1, 2, 2, 0. Okay. This isn't going to work as nicely as I thought. So let's go here, where we know the player. Let's go player position data. And all I want to know is players. And I want to filter. I want to know NFL ID. NFL ID position. Anything else in that player table? Let's take a look. No. No, none of it is actually useful, so we'll go there. So now these are all the players and what their position is. That's fine. 1,600 players. We'll go receiver, data. I always try and keep that ENH as like the last table that we're doing, so we have to go back and change this one. So call this receiver yard data. And this should be PD merge. And take that receiver yard data. And we're going to take the player position data. We're going to say on NFL ID. How, I think this is a left join. just in case, for whatever reason, that doesn't actually exist in the data set. Argument requires, okay, that's just, gotta go back, run this one, run this one. Receiver. There we go. For some reason it was hung up. Okay. Okay, so it's NFL ID X. So on I'll do this receiver. Again, we're going to compare here. Okay, that's fine. Then do receiver. We want to do pandas rename single column. Okay, so I just need to pass it a dictionary. So then receiver yard data dot rename. We want the NFL ID underscore X to just be NFL ID. And then we want in place equals to true. Now we see that this is now NFL ID. Take this all the way down. Back down here. And now we know their position. Now, let's add that. To the model. Right, because now this is no longer hey, we got slight improvement. We got, what was it, 29.7 before to 29.85? Let's see if we is it addition by subtraction? No, so did a slight by knowing who the quarterback was, very slight, but still an addition. So knowing their position adds very slightly to the model. Now we want to try and look at who the other players are and what their positions are. Right, so now instead of players 1 through 11, we're going to need to remove those. Yeah, so let's do that. We'll try and remove some of those out. That's the let's try this. Right, we know the player position. But we need to know not just the individual player, but we need to know the other offensive players that are pass catchers on a given play. So, I started with the yard data enhanced and merged in that, but maybe that's not the right way to do this. Right, so maybe this should come up. So here, player position data. You're now just going to work off of receiver data. I do this. Now I go here. So the only thing we added in was the position. What's the right way to do this? Technically on a play, you could have 5 receivers. Right? So if I try and group this together, I'm trying to think through the best way to approach this, right? We know the 11 players on a given play because we pulled that in from before. But I don't want to know all 11. What I want to know are who are the other pass catchers on the play. And if I go through and just add the position to all 11 of those, then I have to go back through and prune out all the non-receiver or non-pass catcher players. Let's see. Could I do... Let's do this. Call this offensive summary. What I want to do is I'm trying to group the receiver data but what I want to know, and this is where I feel like it can get a little bit messy. I want to know lambda and take this did I close everything out? This should not be here. Same thing for tight ends. Same thing for running backs. This may take a little bit because it's going to go through. It's going to group on these, and that's going to try and aggregate each one. And I want to reset the index. It takes 30 seconds to figure it out, but perfect. So now I want to merge this into the receiver data. So I'm going to take this. We're going to come here. Because what I want to do is, instead of position data now, I want to bring in the offensive summary. And instead of NFL ID, this is the game ID and the play ID. So we know offensive summary here. We saw this is what this table set looks like. This will then let me know who are the how many receivers, tight ends, and running backs are on a given play. Okay, so this. Let's do. Call it that. Now, if I look at so where did those go? Hold on. Right, because we're not using the summary data here. Run this. Should be very quick. Where does your data enhance go? I guess we'll update this. This one doesn't make sense. So here. So even though these are numbers, these need to be in the categorical, because you're not going to have 2.5 receivers on the play or 2.5 tight ends. You're going to have 1, 0, 1, 2, or 3, maybe 4. So we don't want to treat them as numbers. We want to treat them as categories. Position. Where'd the position go? Hold on. Because we did not do this correctly. Okay. So that should be fine. This needs to run. Now we have the position. Now we have a position showing. So knowing receivers and tight ends doesn't actually add a lot of accuracy to a given play. And doesn't particularly help our classification reporting either. So there's still something that we are missing from our model. Do we have the defending team? We do have defending team here in the model. So then maybe we should add the defensive formation information. I have to dig that out of the data. Maybe I'll start there next time as I'm seeing the time now. It's almost 11 p.m. my time. What I'm looking at here is, I guess the summary of everything today is that knowing how many receivers, tight ends, running backs on a given play adds very, very slightly to the predictive power. At least it's not bringing it down like knowing who all the players are. But it wasn't particularly helpful. I guess probably because you're going to get the same information by knowing those player IDs. No, because just the number is not necessarily who those players are. So then maybe it could be worthwhile to know who those players are. I think we'll get more out of knowing maybe some of the defensive information, like is the defensive team in a nickel or zone. Sometimes you can't always identify who zones before the play, so maybe I don't include that. I know motion, you can kind of try and tip it off a little bit, but it doesn't seem to be particularly helpful. Or I feel like you kind of know post snap whether it's going to be man or zone. So we'll focus on defense and defensive formations affecting it next time. Maybe I'll come back tomorrow night and do the same thing here, just because I think it'll be valuable to get time in here. We've only got 14 days left in the competition, and we have not put together a presentation. We don't have, I don't think, good reliability in terms of predicting route combinations. And maybe it's just something that's very hard to predict overall. Essentially, we're seeing on most plays there are 4 to 5 pass catchers available, and we're able to maybe predict 1 or 2 of them on a given play, which maybe is not all that helpful. Like, it wouldn't be. I don't think it's reliable yet. We need to figure out more. So maybe we can get an idea of defensive either personnel or formation, similar to how we have an offensive formation. Actually, let me just see quickly. Is there a defensive formation? Coverage assignments? No, because you can only know that after. Let's see. Defensive team. Defensive cover assignments, matchups. Don't. Yeah. Looking here, I don't see anything particular to defense other than their team. So we will probably have to go through and pull the defensive player information to get an idea of what they are doing on a given play. So it'll probably be very similar to here, where we're going to get a defensive summary. So know like the defensive lineman, cornerback, safety, stuff like that. So like I said, we're about time for what I have available to me today. I can come back and do this again tomorrow, likely in the same time in the evening. Hopefully I can get started a little bit sooner. I know it'll be Christmas Eve, so don't hold me to that. Maybe can do it after. Yeah. So I'll try for some time tomorrow afternoon for this, and then if not, it will be after Christmas to try and put together this. So if I'm not here tomorrow, I hope you all have a Merry Christmas, and then I'll be back on the 26th for sure, and just seeing if we can get a couple more sessions here to try and get better predictive power. Like I said, we've got till January, I believe, 5th or 6th to do this. So we're kind of running short on time, and I'd like to get something that is a little bit more useful to users. So that's all for today. Hopefully the summary at the beginning is good to get you up to speed on what's been happening here. And then, like I said, I'll be here either tomorrow or after Christmas, so we can try and get more here. This will be the majority of my streams. Will either be this or going through and doing training sessions for the reinforcement learning models. So thank you for those of you who are watching this. Please make sure you like and subscribe, leave any comments on things that you want to see or ideas that you have. So hopefully we can try and get these together. And then the next time we'll do is we'll add defensive player information to this, very similar to what I had done here with the offensive summary. Do the same thing for the defense and try and see if that gives us information that would be more useful than knowing who the individual players are and that'll hopefully keep down the size of our data set as well in terms of predictive power. So thank you for being here. And like I said, I'll either see you tomorrow or after Christmas. So thank you. Have a Merry Christmas.